For decades, dark matter has been the ultimate cosmic mystery. It's the hidden framework beneath everything we see, shaping galaxies, guiding the motion of stars, and binding the large-scale structure of the universe. But every time we peek behind the curtain, it evades us. Now, in an astonishing leap forward, the James Webb Space Telescope has delivered unprecedented observations that lift the veil on what dark matter really is, and might be. The moment we've all been waiting for is here. Imagine building a massive castle out of bricks, but 85% of the bricks are completely invisible. You can feel their weight in the castle's stability, but you can't touch them or even see them. That is the universe we live in. Galaxies spin too fast at their edges to be held together by the light-emitting matter alone, and light from background galaxies warps around massive clusters in ways that only make sense if huge amounts of invisible mass are present. This is gravitational lensing. These clues tell us over and over again, something unseen is everywhere and it's dominant. Yet despite decades of effort, no one has ever directly detected a dark matter particle. That's where the James Webb Space Telescope comes in, our revolutionary cosmic time machine. Its infrared eyes peer through dust and capture light from galaxies formed over 13 billion years ago, revealing structures from the earliest chapters after the Big Bang. Webb captured massive, luminous galaxies at redshifts beyond 13, light that traveled more than 13 billion years to reach us, which simply shouldn't have grown so quickly according to old models. At the heart of this revolution lies one spectacular sight, the Bullet Cluster, a dramatic collision of two massive galaxy clusters about 3.7 billion light-years away. Webb's near-infrared images combined with X-ray data from Chandra have created the clearest, deepest map yet of both visible and dark matter in the cluster. By using gravitational lensing on thousands of distant galaxies and tracing intracluster starlight, researchers pinpointed the position of invisible dark matter with unprecedented precision. The observations reveal unexpected clumps and asymmetries, features hinting that dark matter may behave differently than our models predict. So here's the first jaw-dropping twist. Webb's observations don't align with the long-standing cold dark matter model. That model says dark matter particles are sluggish and inert, clumping slowly over time to form a cosmic scaffolding for galaxies. But Webb is uncovering galaxies that are too massive, too bright, and too early in cosmic time to fit that gradual formation history. Instead, what we see suggests galaxies formed faster and more efficiently than the lambda CDM model allows. For example, 3 ultramassive early galaxies converting up to 80% of their gas into stars within 1 billion years after the Big Bang, something the standard theory struggles to explain. Some astronomers now argue these discoveries open the door to alternative theories. One such idea is modified Newtonian dynamics, MOND, which tweaks the strength of gravity at very low accelerations, and which, according to Webb's data, could account for rapid galaxy formation without invoking dark matter at all. Another surprising possibility is that dark matter is not uniformly cold, but instead could be warm, with particles moving faster and resisting clumping, a scenario that aligns better with Webb's early galaxy counts and UV brightness constraints that now set strong limits on particle mass. Then there's a theory even more radical. Dark matter particles might interact with themselves strongly, so-called self-interacting or ultra-self-interacting dark matter. A small fraction of such particles might have clumped early, seeding the rapid growth of supermassive black holes that Webb has also discovered in galaxies less than 1 billion years old, which otherwise seem impossible under standard theory. And it gets weirder, because Webb may have spotted the first dark stars, objects powered not by nuclear fusion but by dark matter annihilation. These hypothetical giants dwarf our sun by factors of hundreds of thousands to 1 million solar masses, and shine with the power of billions of suns. Webb's JADE survey found 3 ancient point-like sources, JADE's GSZ13-0, Z12-0, Z11-0, whose brightness and size are consistent with predictions for these dark stars, offering a tantalizing hint that dark matter might manifest in exotic ways we never imagined. Meanwhile, Webb has also placed the tightest limits yet on axion-type dark matter, particles that, if they exist in the mass range around 0.5 to 2.5 electron volts, may decay into infrared photons Webb could detect with spectroscopy. These new constraints surpass previous lab limits by orders of magnitude, narrowing down possible axion-photon coupling strengths significantly. All of this comes together in a breathtaking picture. Webb's data challenge the cold dark matter model, support alternatives like MOND or warm or self-interacting dark matter, hint at exotic dark stars, and bring direct particle physics constraints into play. While we are not yet claiming we know what dark matter is, for the first time we have multiple concrete clues that force a major rethink. The cosmos is showing us contradictions, and in those contradictions lie the path forward. Looking ahead, the journey is only beginning. Webb will continue observing deep field regions, capturing more lensing and cluster collisions like Bullet, mapping mass distributions with even higher fidelity. Upcoming missions like the Nancy Grace Roman Telescope and the Vera Rubin Observatory's extended surveys will provide larger sky coverage, deeper time domain data, and even faster detection of early cosmic structures, potentially confirming or refuting the competing models we now consider plausible. On Earth, new experiments are searching for axions and other dark matter candidates in labs and underground detectors, while theoretical physicists refine simulations to reconcile Webb's surprising early galaxies, dark star candidates, and axion limits. This is science at its most thrilling. Each finding raises new questions. Was dark matter warm? Did it interact with itself? Are dark stars real? Could gravity itself work differently on cosmic scales? We're no longer in a place of speculation or guesswork. Webb has handed us real data that demands real answers. Closing in on the true nature of dark matter means rewriting the cosmic story. It changes how we understand galaxy formation, black hole seeds, cosmic expansion, and even the ultimate fate of the universe. Everything changes when you realize that most of what you think exists might not be what it appears. And Webb is showing us just how much is still hidden behind the veil of invisibility. So right now, with Webb's new maps of Bullet Cluster, with its deep field detections of early giants and dark star-like objects, with spectroscopic limits on axion decay, we're standing at the edge of a breakthrough. Scientists are racing to test these data, propose new models, and design future observations. And all of us are watching, hoping the next chapters reveal dark matter's identity at last. Because once we know what dark matter really is, we won't just solve a long-standing cosmic mystery, we'll gain a whole new understanding of the invisible hand sculpting the universe. Stay tuned, because this story is just beginning, and the discoveries ahead may forever change how we comprehend everything from galaxies to the smallest particle.